Hey, hello there, calculus folks. This is the lesson for section 2.1 of your textbook. And you'll have to listen to rest all whether it's going to be on the Unit 1 test or the Unit 2 test. Um, and at least for some people, this is the first time they've done one of these flipped lessons. So this is the idea. Usually there's some sort of warm-up, and here it is here. And the warm-up you do first, then you watch the video, which is what you're doing right now, and take the note. Remember that if it's going too fast, you can pause and catch up, or whatever you like, rewind, fast forward, whatever. And then that's as much as you do for homework, and then the actual homework, what you would think of as the textbook exercises, those are done in class. That's the idea of the flip, right? The lesson, the note taking is done after school, and then the exercises are done during regular class time. And this is maybe your first effort at this, maybe not, doesn't matter. In the warm-up, the first thing I usually do is take up the warm-up, and hopefully you've tried these, and if you haven't, you should stop the video and try them. I'm not going to take up 1 and 2. There's your answers. You should have got a slope of 6 and the slope of m equals minus 10, but I am going to take up this one because this is interesting, right? I want to find the slope of the tangent. The slope of the tangent, remember, is the instantaneous rate of change at that point. So it's the limit as, and I could use 2 different formulas, right? I could use this one, or I could use probably more familiar to us because this is kind of what we did in functions, is the f at a plus h minus f at a over h, and probably use that over here, and that's fine. That's fine and dandy. That's the one I'm going to use, and so I'm going to do a little work on the side here. F at a, when I have x squared, I took out the x, I'd fill it with an a. Well, that's just a squared, no problem. F at a plus h then is a plus h all squared. And when I put that into my instantaneous rate of change formula, that what's called the quotient, difference quotient, I think was called in your textbook. That part is this part, a squared plus 2ah plus h squared minus f at a, and that's a squared. And then magically again, right? Whammo, whammo, that's 0. I'm going to factor out an h just like you knew it was going to happen. 2a plus h. The h's will now cancel. Whammo, whammo. I'll divide out, and then I'm left with that limit with the discontinuity removed, which is just 2a. And what's amazing about this is that this didn't matter what a was. This expression, this 2a, is going to give me the slope at any point a. So if I wanted to find the slope at x equals -5, a is -5, I could just put in 2 times -5, I get -10. I wanted to find it at 3, I did 2 times 3, that's 6. And in fact, this slope of the tangent is it's a new function. It's a new function that gives me the slope of the tangent at that point a. So, and that's what we're talking about today, and it's actually not that new, but instead of a, if we just think of it as a new function, we could think of it as, oops, let me erase that. We could think of it as a new function. We could think of it as y equals 2x, right, where x is anything, inputs and outputs. And in fact, what we're going to do is we're going to invent a new notation, not y, because that gets confused with the original function, y equals x squared. So we actually invent a new notation. That's what's coming up in the note here. called f prime at x equals 2x. And this shows f prime shows that we're talking about the slope of the tangent function, the instantaneous rate of change function. This is what's called the derivative function. And maybe you guessed from the title that that's what we'd be talking about. Hopefully you guessed that. All right, on with the note. And nothing surprising here. We'll get through. There's maybe some jargon and some notation stuff that's a little bit scary, but we'll get through it, not bad. The warm-up work leads to a new operation or function called the derivative. So this is an operation we can do. We can take the derivative of a function, or we could think of it as a new function that gives us the slope of the tangent. So here we go. The derivative of f at x with respect to x is the function f prime at x. Or we can say f prime of x, just like f of x or f at x. Those two things mean the same thing, where f prime at x is equal to that IROC definition, that IROC formula that we're used to, except for instead of an a, we have good old x. It makes it a new function, not an expression that we evaluate. It's a new function. So the derivative of f at the number a is f prime at a, and there's the good old thing that we were used to from chapter 1, right? This is like a chapter 1 slope of the tangent thing. And it's not scary. There's the alternate version of the slope of the tangent formula, right? Where we have x approaching a, f at x minus f at a over x minus a, and then sometimes this one was easier, but not always, but the slope of the tangent of a function f at x at the point x equals a. So, and that's what this says. From chapter 1, f prime at x is therefore the instantaneous rate of f at x with respect, rate of change of f at x with respect to x. That is, f prime at x is a function which gives the slope of the tangent for any x. So instead of picking out in individual values a, we think of f prime at x, well, that gives us all the slopes at once. It gives us a new function that gives us all the slopes of f. From the warm-up, we had f at x equals x squared. Then we'd write this f prime at x equals 2x. This was the original function, and then we did our instantaneous rate of change formula, and we did our, the h pops out and we cancel it and we get this. That's the derivative. Other notations. So f prime at x is probably the one I'll use most commonly, but we do use this sometimes where it's y prime at x. Like if we had y equals x squared, we think of, well, if I take the derivative of this, then it's going to be y prime equals 2x. These two notations are more commonly were more commonly used by Newton, where this one, which is read dy by dx, dy by dx, or the change in y by the change in x. You could think of it like that. And that's actually Leibniz. I might have goofed up his spelling, there. Not sure. It should be okay. Leibniz. He's the other calculus guy. And this is very similar Leibniz notation. So this is the derivative of x squared with respect to the independent variable dx. And this notation, although I'm going to use them back and forth, we won't use this one that much, but then later in the course, this becomes very important later, okay? So don't get scared when you see one or the other. We know we're talking about the derivative. Normally, to answer questions like the warm-up, which was just this one, what we're going to do is we'll do this, get the function in general, and then just substitute in regular things. Like you actually did 3 of these instantaneous rate of change calculations from chapter 1. You did 3 of them when really we only needed to do 1 and then substitute into the 2 individual cases. And that's what we're going to do. So we're going to find the derivative, and then we're going to find the individual values at x equals 1 and x equals 5. So what is this going to look like? So we have f prime at x is equal to the limit as h approaches 0 at f at x plus h minus f at x all over h, where No a in here. We're talking about x. And so then over here, if I think of f at x is this function, then f at x plus h is take out the x, put in x plus h, and then I get this this expression, right? This is, maybe I'll tidy this up a little bit, 2x plus 2h minus 1. No like terms there, so that's my expression. So now, what am I going to do? And this isn't that pleasant, but nothing has been that pleasant yet in calculus, has it? It's actually been quite unpleasant. I thought you said, Mr. Restall, that calculus was easier than functions. Well, yeah, it kind of is. It doesn't feel like it right now, though. And that looks awful. Well, that was a bad line there, but it looks awful anyway. Notice that if I put in h equals 0, I'm going to get that disappears and I get 0 over 0. So this is one of those indeterminate forms. And so what I'm going to do? Well, hopefully it's your instinct that when I have roots to multiply by the conjugate. Well, what's the conjugate? Well, the conjugate is a huge mess, right? It's that thing plus that thing. Well, this is 2x plus 2h minus 1, and this is 2x. And oh boy, what a mess. You get the idea, I hope, but I'm going to try and clean this up a little bit. And this is the same, right? This is 2x plus 2h minus 1, and this is 2x minus 1. And then I multiply, and right, the middle terms cancel out. On the bottom, I get h, a nice line there, Restall. I should have used my line tool there. I could have done that. Times garbage. Saving time here. You know, garbage. That garbage goes there. That goes down there. And what do I get when I multiply it out? Well, this times this, it's the same thing. So it's going to be the square root of that thing squared. So they cancel, the root and the square cancels each other out. And I'm left with that minus this thing, 2x minus 1. And notice good things happen here. Now, limit as h approaches 0. Notice the 2x and the 2x will cancel out. Negative 1, subtract negative 1. It's going to cancel out. So what am I left with on the top here? On the top, I'm left with 2h. That's it. And on the bottom, now I guess I actually have to write out all this garbage. 2x plus 2h minus 1 plus 2x minus 1. H's cancel. And now I have an expression where it's okay to evaluate this limit, right? Is it okay for h to be equal to 0 now? Or to get arbitrarily close to 0? Absolutely. This is going to be 2 over. Now notice that this disappears, and I'm left with two of the same expressions. 2 square root of 2x minus 1. So this is, 2's cancel, 1 over 2 the square root of 2x minus 1. So therefore, the derivative is equal to 1 over the square root of 2x minus 1. This is the derivative function. So the derivative of this is this. And so if I wanted to find some individual values, I don't have to go through all that big rigmarole again. I've got a new function. 2 times 1 minus 1. 1 over 2 minus 1 is the square root of 1, which is just 1. So that means the slope of the tangent there at x equals 1 is equal to 1. And I've got my little derivative, slope maker formula here. The derivative is the slope maker. And now I got 2 times 5 is 10 over the square, that's square root of 9 is 1/3. And so at x equals 5, the slope of the tangent is 1/3. Dandy. That's it for this one. And I think I'll pick up example 2. I'll pick up example 2 in part 2 of this video.